In this video, we're going to continue our conversation about refraction, but specifically we're going to look at the mathematical relationship known as Snell's law that tells you exactly how much the light will bend as it goes from one medium to another. We'll also talk about a component known as critical angle, which will be really important when you're going from a more optically dense to a less optically dense medium. Now, to start out, let's just remind ourselves how to predict which direction something is going to bend. In the last video, we used the analogy of a two-wheeled cart, or a two-wheeled axle in this case. If we're going to go from a medium here, say it's water, and is equal to 1.33, that medium causes light to move slower than it would travel through air, n is equal to 1. Those are indices of refraction. So if we imagine this two-wheeled cart, one wheel, the one on the left here, escapes this slower medium first and speeds up. When it speeds up before the other one, it's going to cause that entire axle to bend and change the direction that it moves until the other wheel escapes as well, and then they'll continue off on a straight line. So while that bend is happening, the wheel that escaped first is going to go faster. Now, if I flip this and instead put the slower medium on the top and the faster medium on the bottom, I can draw the same initial incident ray, but now the wheel that hits first is going to slow down because it's going from a faster medium to a slower medium. And it's still going to bend, it's just going to bend in the opposite direction. When it slows down, it bends this way and causes it to travel up like that, decreasing its angle of refraction here, getting closer to that normal line. We're going to use this to help us predict the direction still, but we're also going to add some math to it and get some actual quantified angles here. So say you have a medium boundary here between two different medium. The way that we're going to describe those media is by their index of refraction, N1 and N2. Doesn't matter what two mediums there are, we'll just use one or the other. Now, we have a ray of light that comes in like this, and it's going to bend either down or to the side. In this case, I'll draw it down, but it could go either way. And we're going to define these two rays based on their angle to the normal line. We'll call that theta 1 and theta 2. That gives us four different quantities here that are mathematically related like this. N1 over N2 is equal to the sine of theta 2 over the sine of theta 1. This relationship is known as Snell's law. Notice here that the sine of theta 2 is on top versus N1 is on top on this side. And this looks very similar to an equation that we saw earlier in a previous video. We saw this one here, N1 over N2 is equal to V2 over V1. That's how we initially started talking about the index of refraction as a ratio between the velocities of light in the different media. Well, now we're going to add this equation as well, and really those two can be smashed together to make one long equality, and this is the one that you actually find in the IB Physics data booklet. There are three pieces to it. It's rare that you're going to use all three pieces in one problem. You'll usually use either the index of refraction and the velocity, or index of refraction and the sine of the theta, so the angle piece. Let's look at what this looks like in action. While aiming at a marble at the bottom of a fish tank with water, you notice, or you point so that you can measure the angle of incident rays. What is the angle of refraction? So we're going from air to water. Air has an index of refraction of 1. Water has an index of refraction about 1.33. That's given in the problem. You won't need to memorize a variety of different indices of refraction. Instead, just know that air is 1 and everything else will be provided for you. If we have an angle of incidence, it's going to bend before it gets to the marble. There, we'll define this angle of incidence according to the normal line. Let's say that that's 80 degrees here. So that's provided for us as well. And what we are asked to find is what is the angle of refraction? What is the theta 2 here according to this normal line? The relationship that we're going to use is Snell's law, and we want to solve for theta 2. To do so, I have to multiply both sides by sine of theta 1, and then to get theta 2 by itself, I have to take the inverse sine, and that results in this equation here. This is our first time taking an inverse sine. You can find the inverse sine button on my calculator. It's second sine, gives me the sine to the -1. and then everything in that is taking the inverse sine. So if I take sine of -1 of n1, which is 1, times the sine of 80 divided by n2, which is 1.33, we can figure out what my angle of refraction is. Here, I can see that it bends down. That's how I'd predict it. And that angle is smaller, which is what I would expect. So I can, again, rearrange this equation to solve for theta 2 and then solve with the numbers for that theta 2. It's important to keep track of what you're calling your medium 1 and your medium 2. In this case, I will typically use the nomenclature of where the light is coming from is 1 and where it's going to is 2. But you could go either direction. It's just a ratio that's flipped on the other side. So it always will be equal no matter what you do, as long as you're consistent. So let's try another problem. If the light travels from air to diamond, which has an n value of 2.42, at an angle of incidence of 34 degrees, find the angle of refraction. Same thing as before. We're going to use as part of the equation. Here is our n value, and here is our angles. So go ahead and pause to try to calculate what that theta 2 should be. Rearranging this formula again, I get theta 2 is equal to sine, inverse sine of n1 sine theta 1 over n2, making sure that I'm in degree mode. I have 1 times sine of 34 divided by 1.33, and that will end up giving me 13.4, which again makes sense. If we're going from a more or less optically dense to more optically dense, we are going to bend toward the normal line and end up with a smaller angle. Now, so far, when we've been looking at this, all of the light has gone through and bent. But in reality, there is a lot of light that reflects before the bend happens. I have an example here of this laser trying to go into this acrylic block. There is a significant amount of light that reflects upward to hit my hand right here, even though when I'm firing this in here, a lot of it does bend. Some of it reflects off the top of this block and then bounces into my hand. So there is going to be some combination of reflection and refraction that are going. Reflection is still operating on the same idea that we talked about before. The law of reflection is just incident equals reflected angle. And then the refraction is going to still operate on that Snell's law. We're just adding them together here. Next, I want to talk about what's going on here when this refracted ray goes away. Like what's happening to that, and what do we call that scenario? We call this kind of threshold between the two, where it's able to escape and then it isn't. We call that the critical angle. So let's just imagine a progression here. We have, if we're going from like water to air, going straight out, all of it's going to go through. Then if I bend a little bit, it's going to refract, it's going to bend more. If I go at an even shallower angle, it's going to bend even more. And then there's a certain angle at which it bends so much that it's perfectly parallel with the surface. If it's perfectly parallel with the surface, the angle with the normal line is exactly 90 degrees. That's a right angle. We're going to call this incident angle that results in that 90 degree theta c. That's the critical angle. Anything beyond this is what we call totally internally reflected. Anything beyond the critical angle gives us total internal reflection. We saw that in the animation on the other slide. When this goes far enough that was 90 degrees, any angle beyond that just stays trapped inside and just all reflects back. So we're going to call that critical angle theta c. And we can calculate theta c knowing that theta 2, this angle of refraction, is 90 degrees. No light escapes. So this one point along here is kind of the threshold between light escaping and light not escaping. That's the critical angle. If we wanted to use our analogy of the two-wheeled cart to try to understand how it wouldn't escape, imagine that this wheel that escapes first starts going faster, and then it kind of laps the other wheel and then actually comes back into the slower medium before the other wheel even has a chance to escape. We get this total internal reflection. Let's watch that one more time. So beyond a certain angle, this thing is not escaping at all. The light stays inside. And we can calculate this critical angle knowing that 90 degrees is going to happen here at that theta 2. We solved for theta 1 here, just rearranging again this equation to solve for that theta 1. And we get inverse sine of n2 times the sine of theta 2 divided by n1. Well, we know that the sine of theta 2 is 90 degrees, and we're going to call this sine of theta 1 the critical angle. So all we need to know are these indices of refraction, the index of refraction for n1 and n2, and we can plug those in and solve for it. So really, if you really think about it, a 90-degree angle, the sine of 90 degrees, if you're in degree mode on your calculator, will always give you 1. So n2 times the sine of 90 degrees is always going to be just n2, which means our critical angle formula simplifies down to this. This is not a formula that you're going to be given on a test for the IB exam or for any exam in this class. So I would recommend just use the technique of just plugging in 90 degrees and taking that where it takes you to solve for the other angle. And this will only happen if you're going from a more dense to a less dense medium. You will never have a critical angle if the medium that you're starting in is less dense, because the bend is going to go the other direction and it will never be trapped like it is here. So let's solve this for glass. If I want to know what the critical angle between glass and air is, I know that N1, where I'm starting, is 1.52, and 2 is 1. I know that theta 2 has to be 90 degrees. So if I plug that in, just keeping everything the same here, not even just solving the equation for theta c yet, I can plug in 1.52 for N1, sine of theta c, and then 90 degrees for theta 2, and 1 for N2. Rearranging, knowing that sine of 90 degrees is just going to be 1. This ends up giving me the inverse sine of 1 over 1.52, which is 41.1 degrees. So anything beyond 41.1 is trapped inside the glass. And anything less than that is somewhat going to escape, and then the rest will be reflected back in. So you might be wondering, why would this matter? This feels like a weird scenario that is just kind of this quirk of how refraction works. Well, it is an important application, both for some interesting things. There's a phenomenon known as Snell's circle. If you're underwater looking up, like you're a fish here looking up, you'll actually see just a circle of sky because your eyes can only see from where the light is coming. It doesn't know how things have bent along the way, which means that the light coming from the horizon to get to your eyes has to bend like this. Anything shallower than that is going to be totally internally reflected. So beyond this circle, you're actually seeing the reflection of what's down in the ocean instead. So if you're deep enough and you look up, so say you're scuba diving or snorkeling really deep, you might see Snell's circle. A more interesting and probably useful application is something known as fiber optics. A fiber optic cable is used to transmit light as data. Here I've got, this is not a fiber optic cable, we'll call this a light pipe. It's a way of demonstrating the same concept. If I aim this laser into my light pipe, you can see a little bit here how that laser is bouncing back and forth and is trapped inside, and actually makes it all the way to the end of this light pipe. You can see that bright spot as it's coming out. So what we can do is then make miles long versions of this, very, very thin. So there are these thin glass hairs that you can transmit light in a series of ones and zeros to transmit data very, very quickly. That's much faster than transmitting data on an electrical cable. So that's faster than electricity, and you can transmit data very quickly. You may have heard of like fiber internet. That's what we're talking about. Fiber optic cables. It's using total internal reflection to trap light inside these glass hairs to transmit it from one place to another over a very, very long distance. In a sample IB question that's been asked in the past, a light ray is incident on an air-diamond boundary. The refractive index of diamond is greater than 1. Which diagram shows the correct path of the light ray? So know that it's going slower in diamond than it is in air. Think about your two-wheeled cart. Which one of these is possible? All right, we can rule out B pretty much right away, that these two, it can't work like that because there's a difference. There has to be a bend. If we looked at D, a two-wheeled cart, going like this would mean that it had to speed up in diamond to cause that turn, and we know diamond is going slower. And then same thing in C. In this case, if a wheel on the left side here hit air, it would speed up and bend the other direction. The only one that actually could be possible is A. In this case, it's total internal reflection. It's kind of thrown in here to try to throw you off. But A, it's a shallow enough angle that it totally bounces all the way back in. So the takeaways for this lesson, you should be able to mathematically relate the angles of refraction to the indices of refraction of the materials. The larger the difference in that index of refraction, the bigger the bend, and that Snell's law will relate that. You should be able to describe the phenomenon of total internal reflection and some examples of why that it's important. And you should be able to calculate the critical angle of incidence to create this total internal reflection where light cannot escape the medium.